Dr. Beatrice Magnani.
Thank you, Mitch. And thank you, everybody, for inviting me here. It's a real pleasure to be here at Marshall University and to have the opportunity to talk a little bit about the research I've been conducting in the last 15 years since my postdoc days as a postdoc in the CDROM project that Mitch just mentioned. So before I go on, since the talk is going to actually be a collection of results throughout my scientific career here in the United States, I want to acknowledge the funding agencies, the National Science Foundation, the U.S. Army Corps of Engineers, and the USGS. And the list of colleagues that have contributed to the results of this will be too long to be acknowledged, but they will be acknowledged throughout the talk. And of course, GeoPRISM with the two focuses. So what I would like to talk to you today, it's about the role of, rather the legacy that paleo structures play in the tectonic history of continental region. And particularly the intraplate region as the plate boundaries are amalgamated inside the continents. And I'm going to try to make the case that these paleotectonic structures remain preserved in the core of continents, and particularly the mantle plays a role in then playing in focusing the deformation, sometimes the seismicity, and in other cases the magmatism, long after the tectonic history associated with the event that formed those boundaries, as long ceased. Okay, so let's start with our history. So by studying the continents and by studying the structure and the age of rocks that form continents, geologists have long recognized that continents are formed by the amalgamation of terrains. And this amalgamation of terrains often follows the dispersal of these terrains. And the cyclic dispersal and amalgamation of these terrains is what we call the Wilson cycle. What I'm showing here, and this is a slide that I borrowed from Harm van Avendonk, are the Appalachians. And we know that the terrains in the Appalachians are bounded by sutures. And we know that these sutures are the results of the collision of these terrains up against the pre-existing continents. We know also that after the collision that resulted in the Appalachian mountain belt, the following rifting that dispersed Pangaea, the supercontinent, followed the all-terrain boundary, suggesting that there was what we call an inheritance in that rifting process. And it's exactly that inheritance process that I want to discuss today. So when we look at the North American continent, the North American continent is a very old continent. It's actually a continent that contains the record of the assembly that since the Archean time. So we have the opportunity to study this inheritance process for a long time. And I'm going to show you here a series of slides that are taken from Steve Whitmire and Carl Karlstrom that are showing how the Archean core of our continent grew by a sequence of accretion to the southwestern edge from about the Paleoproterozoic all the way till about 500 million years ago. And what you're going to see in a quick sequence, and I'm going to describe slowly how that will happen, is how the Archean craton will see this amalgamation to the south of a series of Proterozoic terrains. And so we're starting here with the accretion of Mojave and the Yavapai province to the south at about 1.7 billion years. So these are billion years. So this is a very long time ago. And then, apparently after the suturing of the Yavapai terrain, there is the stitching and stabilization of this terrain by orogenic magmatism that is pervasive throughout the entire terrain. And then again, the Mazatzal, a new juvenile terrain gets accreted to the south, and then there is another magmatic event at about 1.6 billion years. And then there is a lull in the tectonism. What we see that lull is interrupted by the accretion of the granite rhyolite province at about 1.35 billion years. And after that accretion follows a pervasive episode of magmatism. This episode of 1.4 billion years, that is about 1.4 to 1.35 billion years, is pervasive throughout the entire southern edge of this continent that we call Laurentia. And it's pervasive, and we find evidence of this magmatism all the way into Baltica, that is on the opposite side today of the Atlantic. But there was at that time in the Proterozoic was one single continent with Laurentia. And then and this is actually at this point there is another collision, and we form the Granville orogen, which is also what we call Rodinia. This is the formation of a supercontinent called Rodinia, and is the collision. This is the collision that marks the collision between Laurentia and South America and the African Cretan. This is now the formation of a supercontinent that is stable for a certain amount of time before it starts breaking apart. And again, at 1.3, the intrusion of the granitoids into this new formed supercontinent. And then the supercontinent destabilizes and starts breaking apart. Again, you see this cycle of supercontinent formation and then dispersal. And we know this has happened several times throughout the history of our planet. And the formation of the mid-continent, and then again the rifting along the western margin of Laurentia, and then the formation of the rift along the eastern margin of Laurentia, and the formation of the Rome Trough, and finally the break apart of Laurentia and the opening of the Iapetus Ocean. And what I'm going to talk today about, and the formation of the Oklahoma Allocogen, the Reelfoot Rift, and the rifting away of the Argentine of this portion of the Laurentia continent that we find today in the Argentinian Precordillera. And so today what I'm going to talk about are I'm going to take you to a place in the western United States where we observe how this assembly structure inherited from the Proterozoic history of our continent still play a role in the western United States. I'm going to take you in this area here in the Reelfoot Rift region, where instead the extensional structure at 500 million years old are still playing a role in the seismicity. And then I'm going to take you here with showing some preliminary results of the across the eastern margin of the United States, to show you just the results that we collected this summer as part of the eastern margin of the United States community seismic experiment. Okay, let's start. So we're going to go from west to east. And we're going to start with the western United States. When we look at the velocity structure, so this is a map of the velocity structure of the P wave and S wave velocity structure at 90 kilometers. So we are in the upper mantle of our continent. And what you see here in blue, you have, I must have lost the velocity structure, the velocity scale. But what you see here is that in blue, you have the fast velocities that characterize the cratonic North America. This is the fast. And we interpret this as a cold mantle. And what you see instead to the west, you see the slow velocities in the upper mantle of what we call the tectonic North America. This is also what we interpret hot mantle. Okay? And so this is identified also in the P wave velocity and also in the S wave velocity. At the interface between cratonic North America and tectonic North America, we also see these fingers of cold or slow mantle that is actually penetrating the fast mantle. And this trend, these fingers of slow mantle, seems to trend in a northeast southwest directions. And we're going to see what these northeast southwest trends are. And we're going to focus in an area that is roughly exemplified by this block. So this area, these northeast southwest trends, are what we already seen. These are the margins, this is the grain of the Proterozoic assembly. These are the margins, these are those sutures between the Yavapai and the Mazatzal terrains that were accreted during the Paleoproterozoic up against the Wyoming and the Archean craton. And in particularly, what we are going to focus along this suture here, which is the suture between the Yavapai and the Mazatzal terrains. And we're going to see that along this suture today, we observe an alignment of volcanoes that are Cenozoic and Quaternary in age. And this is what is called the, in black, what you see here, these are the volcanic centers that characterize the Chemetz lineament. And what you see here superimposed on top of under the volcanic centers is that same velocity structure in the upper mantle with the p-wave velocity at 80 kilometers that I showed you in the other slide, suggesting that there is a slow velocity mantle that is aligned on top of an alignment of volcanoes that are Cenozoic in age. So to study so suggesting that these you already see that there is an inheritance in the alignment of Proterozoic sutures together that is somehow focusing the magmatism along this trend. However, we don't really know, by looking at the rocks, we only see that there is a change in chemistry and in rock type at the surface. But we don't really know what that is represented, the structures that are representative of this suture at depth. And so in order to understand what characteristics are typical of this suture as part of the Rocky Mountain, of the CDROM project, we actually investigated exactly this region. And in this map, I'm showing in colors the different provinces and terrains of the Archean and the Proterozoic terrains. In blue, this is the Yavapai, and this is the Mazatzal. And the shading here is suggesting the zones that have been invaded in the mantle, subsequently during the Cenozoic and especially in the Quaternary. And what you're seeing here, these are the different, the different ages of the provinces. And so the CDROM project shot and investigated exactly the nature of this suture, trying to understand the inheritance of this suture and the role they played in the Quaternary and in general Cenozoic deformation and magmatism. And what I'm going to show you, particularly I'm going to show you the velocity structure as derived by a refraction profile, seismic refraction profile, that goes from New Mexico all the way up to Wyoming, crossing from the front of the Rocky Mountains all the way up to Wyoming. And I'm going to show you a seismic reflection profile located right here across the Chemetz lineament. And I'm also going to show you passive source data across the two sutures, the suture between the Cheyenne Belt, across the Cheyenne Belt between the Archean and the Proterozoic terrain, and between the two Proterozoic terrains. And so this is the crustal structure as imaged by the refraction profile. What you see here is that so these again are velocities, and the warm colors are slow velocity, the cold colors are fast velocities in kilometers per second, and this is depth, and this is the distance along the profile. So from the south to the north, this is a highly vertically exaggerated profile, but basically a 7.5 to 1, and this is a 1 to 1 profile. What you see here is that the upper crustal structure is dominated by the laramide uplift, and the slow velocities correspond to the basins, whereas the sedimentary basin and also those granitic plutons that were intruded during the 1.4 granitic magmatic event that we described earlier. And in addition, what you see is that the moho that separates the crust from the mantle seems to be much shallower under the Chemetz lineament, which is this portion here of the profile, than under the rest of the other suture. So when we look at the, also across the entire profile, we also see, so we see that the velocity of the upper mantle under the profile appears to be much slower under the Hermet's lineament than across the rest of the profiles. In addition, if you look at the heat flow, this is a map of the heat flow along the entire profile. The Hermet's lineament appears to coincide with also high heat flow located right here. So the coincidence of high heat flow along the Hermet's lineament, low upper mantle velocities, and slow and a high topography localized there suggests that so these are the coincidence. There is a low upper mantle velocity, a high heat flow that coincide with the Hermet's lineament right where the crust appears to be thinned. So when we go and look deeper, and we use the teleseismic data, and now these are seismic data that allow us to see much deeper into the lithosphere. Now we're looking at a depth of about 250 kilometers depth. And we're looking here across the Hermet's lineament and here across the Cheyenne Belt suture. So what you will see across this, the Hermet's lineament, we're going to focus here, what we see is that there is a large seismic anomaly, velocity anomaly, a slow velocity anomaly in the mantle under the Hermet's lineament that extends all the way down to about 150 kilometers. And so not only we see slow slow velocities just below the moho, but we see these slow velocities extending well into the upper mantle. And also, so the coincidence of slow velocity in the upper mantle, high heat flow at the surface, and obviously the occurrence of basaltic volcanism suggests that the mantle is actually, it has high temperature right there. Now, so this is what the seismic data and the heat flow and the geophysics data suggest. So that under this suture, there is, under this, this grain that is inherited from the Proterozoic event, the mantle is hot. But why is the mantle hot in this region? Why is it that the mantle is focusing magmatism along this structure? So to look at, to understand why right here, we had to go and look in the crust. And when we looked in the crust with the reflection data, we shot a seismic profile that was about 120 kilometers long profile right here. What we found is we found a series of signature within the crust. And now we're looking just at the depth of 50 kilometers, but we're looking with a much higher resolution. And what and when we went to interpret this reflection profile with the nearby geology outcropping along the uplift of the Rocky Mountains, we were able to identify, the transparent zones as the 1.5 granites, these large, long reflectors as the great unconformity, the deformation in the middle crust as the naps that are outcropping in the laramide uplift, and these bright reflectors, as we interpreted them as the recent intrusion associated with the Hermet's lineament, that are overprinting what we interpreted as a divergent suture that was formed by the collision of the Yavapai and the Mazatzal terrain. And so when we bring all this together, so you have the divergent origin, with the Yavapai crust that is dipping under the Mazatzal crust, and now there is a mafic underplate that is being formed much later during the 1.4 anorogenic event, and is now overprinting the suture, and then much later the intrusions of the basaltic seals that is overprinting the entire suture. And so we came up with a tectonic evolution that involves the two terrain, the Yavapai subducting under Mazatzal, the collision of the Allandark terrain up against the Yavapai continent with the formation of the divergent origin, and then at about 1.65 billion years. And then much later, at 1.4, the intrusions of this granitic anorogenic magmatism with a minor basaltic underplate, and then much later, uplift, erosion, and the intrusions of the basaltic material that is associated with the Cenozoic Chemetz lineament. And so the take-home point here is that, from this portion of the North American continent is the Yavapai-Mazatzal boundary coincide with the divergent suture that is preserved in the crust, but also in the mantle, right? So, and that this suture, this divergent origin and this suture is preserved in the crust is not surprising. We expect the crust to preserve this type of structure because the crust is brittle. But the fact that the mantle will preserve such a suture at time scale that are in the billion years time scale is much more surprising because the mantle tends to behave in a plastic way at those time scales. So in addition, this suture today is providing a pathway for magmas to intrude the continent and reach the surface. And suggesting that, therefore, in the western United States, this Paleoproterozoic grain is actually controlling the ongoing activation, the modification, and the metasomatism of the upper mantle and the reconstruction of the overlying crust. So the mantle actually is playing a major role in the activity in the crustal deformation. Okay, so we were just looking at this region here. We're now moving into another region of our continent, and we're moving into the central United States. There, we're going to see a similar story, but with different tectonic conditions. We're moving into the central United States. We are in the Mississippi embayment. And here, this is Memphis. This is the Mississippi River that flows from Cape Girardeau through Memphis on its way to Louisiana and to the Delta. So here we see the same structure, but in this case, they are buried under the thick Mississippi River Valley sediments. And so they are not outcropping, so we don't see them at the surface. And so they are buried, and so this is the structure, the front of the Granville assembly that formed the supercontinent Rodinia. And then we see the disassembly structure. These are the opening of the Iapetus Ocean, and therefore these are the Reelfoot Rift in green and the Alabama-Oklahoma transform. And then we have, associated with this rifting, which is pretty much what you will imagine the African rift, where a continent is rifting apart. There is a lot of magmatism associated with this type of rifting. And so this has been an image at the base of the crust. This is what we call the rift pillow. And I'm going to show you in the next slide what this rift pillow looks like. But it's a structure that extends pretty much under the northern embayment and is pretty thick, about 20 kilometers thick. And then we have the assembly. As we know, the Rodinia rifted apart and then got assembled again, and that was Pangaea. And the assembly of Pangaea is marked in this region by the structure of the Ouachita Fold and Thrust Belt. Now, so as I said, the magmatic event that was associated with the rifting of the Reelfoot Rift, left into the crust a layer that we actually identify as a fast layer at the base of the crust that we interpret as a mafic rift pillow. So this is the basaltic material that ponded at the base of the crust that intruded the crust from beneath. So this rift pillow plays a crucial role is located here in actually focusing the formation in this region. So we care about this region because this is actually the location where the New Madrid Seismic Zone is located. The New Madrid Seismic Zone is where about 200 years ago, 4 of the largest earthquake ever recorded, actually ever felt on our continent, occurred. In the winter of 1811, 1812, 4 magnitude 7 and greater struck in this region. And today we know that those 4 earthquakes were not just freak event, but were just the last of a series of large earthquakes that seems to have struck this region every 500 years. And today we actually monitor this region, and we know that it produces about 200 earthquakes with magnitude between 1 and 4. So the New Mexico seismic zone is the largest intraplate seismic zone of North America. It is extremely enigmatic because it's about 200 kilometers far away from the nearest plate boundary, where most of the seismic activity on our planet occurs. So it occurs along 4 faults that define what we call a restraining band, and is monitored today by about 120 seismic stations operated by the Center for Earthquake Research and Information, and about 13 geodetic stations that monitor the movement of the blocks that characterize this region. And some of these monuments, the geodetic monuments, are on unconsolidated sediments, and some of them are on basement. What is puzzling about this region is that despite the high level of seismic activity, we see absolutely almost no deformation at the surface. And I'm going to talk about a little bit more about the science of this at this evening talk. So if you want to know more about this and what motivates a large project that I just finished here, you can come to tonight's talk. But what is puzzling today is that in this region, we see large seismic activity, but we see no deformation at the surface. So we usually observe large earthquake where there is mountain formation processes. And instead, we see no surface deformation, no subsurface deformation. So this is quite the puzzle for geoscientists. Another puzzle is what is driving this deformation? We're not a plate boundary, so what are the forces, what are the mechanisms that are generating this deformation? So among the deformation driving mechanisms are, they have been invoked, the anomalous structure in the crust, which is this rift pillow that seems to be centered right under the seismicity, that is capable of localizing the stress and the strain, actually. So you already see the inheritance of this Paleozoic structure that is capable still to apparently localize the seismicity in the crust. But again, because the seismicity seems to be a very recent phenomenon, we need something that triggers this deformation just recently in the Holocene. And so whatever mechanism is invoked requires something that perturbs the stress field, or what we call the Holocene trigger. And that has been invoked, has been suggested that it is the sinking of the Farallon slab that reaches the depth, the mantle right under this region about at the right time. Or the retreat of the glaciers that allows the lithosphere to rebound back in this region, in the Holocene. Or a possible Holocene change in plate motion are the three. So the three possible Holocene triggers. So is the combination of an anomalous crustal structure with the Holocene trigger that the two of them combined allow this seismicity to be localized here. In order to understand, and in fact, if we look at where the quaternary deformation Pleistocene and Quaternary and Holocene deformation has been detected, we see that it's roughly, localized on top of the rift pillow, suggesting that indeed the rift pillow plays a role in concentrating the stress and the strain. However, the deformation that we observe at the surface is not enough and doesn't reconcile. It cannot be reconciled with the return time of the of 500 years that we observe from paleoseismic data. And so what I'm going to show you are some of the results that we obtained from the Mississippi River Project. That is a project that acquired about 950 kilometers of acquisition along the Mississippi River. We acquire high-resolution seismic reflection data looking for faults in addition to the one that are active today. And I'm just going to show you two examples to show you how this extensional structure is still playing a role in focusing deformation. One is going to be here, and one is going to be at the edge of, at the southern edge of Laurentia. And so these are reflection, this is a seismic reflection data profile. This is now just a depth of about 1.3 kilometers. So we're looking at a high resolution seismic reflection data profile that is about 15 kilometers long, and is located right north of Memphis. So we are outside the location of the rift pillow. So we're just at the edge of the rift pillow, but outside. And what we see here, we see that the Paleozoic and the Cretaceous sediments have been deformed, and that a fault is actually cutting across all the tertiary sediments and deforming the quaternary sediments, suggesting that this fault has actually been active very recently. And if we look just at the surface to look at the very recent deformation, we see that it actually deforms the base of the quaternary alluvium, suggesting Holocene deformation. And again, if we look at even more detail with a different type of data that we call sub-bottom profile data or chirp data, this allows to look now at the very first 10 meters of sediments, but with a much higher resolution. And what we see there, we see that some of these sediments might have been deformed right on top of this fault. And what we observe also is that, so all these observations suggest that this fault has been active very recently, and that the other observation that I want you to remember is that when we look at the offset along this fault, we see that the offset on the top of the Paleozoic is about 130 meters, and that offset decreases with the age of the sediments, as the sediments become younger, which suggests that this fault has been active repeatedly throughout time. Okay, so, and this fault actually, we observe it repeatedly along the Mississippi River, and we can follow it from this location here, where it was first identified in 2001 by a USGS survey, along the river in 5 locations, and we follow it for about 45 kilometers. And we called it the Mimon-Shelby Fault. Is it falls along the eastern margin of the Reelfoot Rift, identified in the subsurface. And so a fault that is this size and this rupture length is suggestive of a moment, capable of a moment magnitude of about 6.8. Suggestive that is, so if this fault ruptures all in one event, it might actually generate an earthquake that is, has a magnitude of up to a 7.2, suggesting that this fault might be much more dangerous and hazardous to Memphis than the pneumatic seismic zone itself. We know by liquefaction evidence right here that there is evidence for seismic activity in the Holocene about 4,000 and 2,000 years ago. Okay, so now instead, and this fault is located along the east margin of the Reelfoot Rift. And now we're going all the way down to the southern edge of Laurentia. This is along the, what has been identified as the Alabama-Oklahoma transform. This region has been identified also as an area where a lot of magmatism is observed. And here, I'm going to show you this line here that is down here. Again, the same depth, about 1.5 kilometers in depth. And what we're seeing here now, we're seeing a fault that cuts these are the Cretaceous fault, the Cretaceous, the top of the Cretaceous sediments, and this fault actually cuts all the way down to the Cretaceous sediments in a normal motion. And what we see is that we can follow it all the way up, and I'm going to show you this. We observe, this is actually a close-up of that region, we observe tilted sediments right at the top, suggesting that this fault also has recent deformation associated with it. And if we look at the very shallow portion, like we did for the other fault, using, again, the chirp data set, we're going to see at a much shallower depth, but with a much higher resolution. We're going to look at higher frequencies in this case. I'm going to show you two short sections right in this location. So these short sections show the Holocene sequences, and these are this is the unconformity that separates the Eocene sequences, and this is the unconformity that separates the Eocene sequences from the Quaternary alluvium. And what you see here is that several faults are actually cutting that unconformity, suggesting that there is Quaternary deformation in this region. And indeed, the Quaternary deformation is confirmed by paleoseismic evidence nearby. These are two venting fields. These are a liquefaction field, the Desha County and the Ashliff County field, where 3 major venting episodes have been identified, with age about 7,000 years. And the size of the liquefaction right there suggests that there is a seismic source, and we have suggested that the fault we identify is is exactly the fault that we imaged along the Mississippi River. Again, suggesting that there is activity, Quaternary activity, focused along the Alabama-Oklahoma transform. So again, a few take-home points. So all the faults that we identify, and I just showed you 2 examples. We've actually identified several other faults along the river, inside and outside the rift pillow region. So all these faults show a long history of deformation. So the faults that have been active in the Tertiary seems to continuously be active also in the Quaternary, and possibly since the Upper Cretaceous. And so we identify Quaternary deformation both inside the region of the rift pillow and outside the region of the rift pillow. And so we also notice that Quaternary deformation is accommodated along paleotectonic structure. We see the east margin of the Reelfoot Rift, and along the Alabama-Oklahoma transform. But if you notice, not all the paleotectonic structures are being reactivated. In fact, we couldn't find any reactivation along the Ouachita Fold and Thrust Belt. And so obviously there are questions that this finding raises. One of them are the implications for the seismogenesis in the central United States. So considering that the distribution of late Pleistocene and Holocene is not just within the rift pillow. Since it extends outside the rift pillow, then obviously there are other structures embedded within the crust or in the upper mantle that are capable of focusing the deformation. So then either the rift pillow extends beyond what we've been able to image in the crust, because we've imaged only this area, or there are other structures that are capable of focusing the deformation. In addition, we have to understand what is the difference between the extensional structure, like the rift pillow and the Alabama-Oklahoma transform, and the Reelfoot Rift, and the Ouachita collision, because some of them are capable of being reactivated in the Quaternary, and some others are not. What we notice, obviously, is that the Alabama-Oklahoma transform and the Reelfoot Rift are lithospheric through-going structures. They involve the mantle. Instead, the Ouachita collision was what we call a soft collision. It didn't have an involvement of the mantle, suggesting, therefore, again, that the mantle plays a role in the deformation that occurs in the crust. And again, the question, about the mafic pillow, is the mafic pillow a structure that is unique to the New Metric Seismic Zone, or is just, ubiquitous? We don't have an image of the central United States yet, but the Earthscope is actually arriving there, and some of the images are emerging. For now, I'm going to show you a very old image that is extracted from Rail 1989 compilation of refraction profile across the Great Plains from the front of the Rocky Mountains all the way to the Appalachians. And what we see here, and this is, I want you to notice that this, the control point are just these, short, lines here, 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 and here. So this is a not very well constrained model. But what I want to show you is that there is a high velocity lower crust across this entire region here. And this is where the rift pillow is located. Now, Brandenschmand and Liu have just produced, using Earthscope data, this map of the lithospheric structure under the United States. And what you see here, this is these are surface wave velocity between 1 and 0 kilometers. So these are just the sediments. This is just the 0 to 3 to 11 kilometers. But what I want you to focus is here. This is the velocity within the lower crust. And the central United States is right here. This is the embayment. And the embayment shows, again, fast velocity in the lower crust, not just centered under the rift below, but extending all the way down into the central embayment and southern embayment. Suggesting, again, that where we observe quaternion deformation, there is a fast velocity layer in the lower crust. OK, and now we are finally moving, and I'm almost done, into an area where we just collected data just to look at the inheritance of the opening of the rifting. And this is the opening of the Atlantic, and this is the East North American margin. This is an area that recorded 2 full Wilson cycles. So this is a prime location to study inheritance. So in this region, so we know these are images taken from Bill Thomas' paper in 2006. What you see here, these are the structure formed during the assembly of Rodinia. So this is the suture between the continent and the Greenville origin. And what you see here, when Rodinia broke up, the embayments and the promontories follow that suture established during the suturing of Rodinia. And then the following assembly of Pangaea seem to follow again the same embayments and promontories, especially in this region. And then the rifting, again, if you look at it, again followed the same trend, suggesting a strong inheritance into these 2 Wilson cycles, opening and closing. And so what we did, and this is actually strong inheritance, and I'm going to mention there are several observations that we can make along the margin to point out the inheritance. I'm just going to make one, and this is how the Appalachian structure matches the structure that we observe along the Atlantic rifting. And these are 2 profiles, the Lasse and the Edge, right at the edge between the northern Appalachian and the southern Appalachian. What we see there is that the onshore transition between the northern Appalachian and the southern Appalachian corresponds offshore with 2 different thickness of basins, one to the north that is 15 kilometers, and one to the south that is 8 kilometers. That suggests that the 2 completely different elastic thickness of the lithosphere that seem to have been inherited from the continent that broke apart. And so when we look at this now is a magnetic image of the margin. What you see in black here is the coastline along the margin. This is Florida, this is Cape Hatteras, and this is New Jersey. What you see here is the completely different signature, magnetic signature of the continent versus the ocean. And what you see here, these are the signature of the magnetic anomalies that characterize this margin. And so here you see the characteristic signature of the oceanic crust versus the continental crust. What you see here is the Brunswick magnetic anomaly that seems to extend offshore, and has been interpreted as the suture between the Saguenay terrain and the Carolina terrain, one of the interpretation. And here we see the East Coast magnetic anomaly that seems to mark the breakup of the continental crust and the first appearance of the oceanic crust. And then the Brunswick, the Blakesport magnetic anomaly, this very enigmatic structure that seems to be a ridge that has been a jump in the ridge, that occurred during the breakup. And so we designed the INAM community seismic experiment to span right across this structure to capture the the margin from the continental crust all across this rifting structure into the mature oceanic crust. And what we did there, we used land acquisition and a marine acquisition with land receiver, land shots, broadband OBSs, and marine multi-channel seismic data. And these actually, I wanted to show you here how this acquisition spans both the unextended crust, the stretched continental crust, the thick magmatic crust that in the oceanic crust, and then the normal oceanic crust. And I'm going to show you some portion of the just acquired data. We just acquired this data, so we have not analyzed that yet. So this is a portion of the reflection data going all the way down to 12 seconds. And this is actually all along this portion of the margin. This is right on top of the Blakespoor magnetic anomaly, showing thick oceanic crust right on top of this magmatic anomaly. And these are OBSs from the two major deep lines. So this, the OBS 207, showing the two different thickness of the crust, the stretched crust to the west and the thin crust, oceanic crust, to the east. And then OBS 122 just sitting in normal oceanic crust here. And then the land data. This is the data has recorded along the northern line. This is the shot along the coast recorded by 420 stations. And what you see here are the arrival recorded from the refraction in the mantle and the reflection of the top of the mantle here. I show the structure, a very, this whiff here that you see, there's a reflection right on the top of the edge of some tertiary basin located right here in the middle of the Carolina terrain. And now right at the opposite, what you see here now is the arrival of the reflection of the top of the Carolina terrain, Moho. And again to the south, again, we can see beautiful arrival from reflection from the Moho, to the south. And so these data are just waiting to be, and these data are available to the community, available for everybody who wants to analyze them and do science with them. So that's why we collected them. And so to conclude, so what we observe is that both the assembly and the rifting paleostructures are preserved in the mantle and in the crust, and especially in the mantle, suggesting that the mantle doesn't heal, not even at the geological timescale of a billion years. And that this grain established by these structures is capable of focusing the magmatism, the mantle's metasomatism, and the formation and the seismicity in the crust that is overlying the mantle. And this happens even long after the tectonic event that generated those tectonic structures has ceased. And with that, I will take questions.
Questions for
I think if you want to ask a question, you have to go to the camera. No?
I think we're okay.
Okay, you're fine. Okay.
The preservation of history and everything that happens, even DNA in our bodies is preserved. I mean, it diffuses away, the information diffuses slowly away, and new information is like the same thing. Process of geology, they really always thought that they wouldn't be preserved. It's just the fact that you can see them, identify them, talk about them. That's what's interesting.
Well, I think what it was surprising, for example, when we shot the profile along the Mississippi River, I was expecting to see deformation associated with the Ouachita front. So what that really, and this is something that we're going to have to investigate further, because we don't observe any reactivation along the Ouachita. So what is interesting is that not every structure they might be preserved, but they don't seem to be continuously playing a role in the modern reactivation, or in focusing the deformation, in refocusing the strain, the seismicity, the magmatism. So that's why I'm saying that what is important is the role that the mantle plays in that deformation. So it has to be, and this is obviously is a working hypothesis, is that the event has to involve the mantle, the continental mantle, in order to be able to be preserved and to play a role in the subsequent deformation. Because the Ouachita apparently didn't involve the mantle, and in fact, it doesn't seem to be a structure that is reactivated in the Quaternary. So it is true that these structures might be preserved, and in fact, we see them preserved in the crust, but they don't play a role. So there is no inheritance, in those structures. So this is what is striking. So the Hametz lineament is sitting on top of a suture that obviously involved a deformation and some metasomatism in the mantle. So if it was just, so this is actually what is striking to me, is that I would imagine that the mantle at the time scale of billions of years will heal eventually, will plastically remove that type of structure. The crust will preserve it because it's brittle. But the mantle should remove that deformation, remove that scar. And instead, it doesn't seem like it does. And it is the mantle that plays a role and that causes the deformation in the crust. It's like the crust seems to be riding along somehow. But it's it's the deformation that we observe, right?
I remember you saying that, and also, yeah, because I wouldn't have it. Apparently, the mantle is more slow-moving. We think it's not rigid. It's a lithosphere. Apparently, it just doesn't change that fast. It's not right.
Well, the mantle has a different behavior depending on a viscoelastic behavior, depending on the time scale we observe it, right? Obviously, it's brittle in terms of when we look at the mantle at the time scale of earthquakes. The oceanic mantle is hosting seismicity, so it behaves in a brittle way. But if we look at the mantle at a time scale of the elastic rebound, for example, we know it's capable of plastic behavior, in behaving in a viscoelastic way. So the behavior of the mantle obviously changes depending on the time scale we observe it over. So at the time scale of billions of years, it should definitely behave plastically, right? So that's why, it is surprising.
But even though it's plastic, it still stays relatively plastic. It stays the same. There's a lot of vertical movement. So what happened a long time ago moves over here, and then what's happening now is, so that's why you say you can't see any evidence of that.
Well, we think that the crust and the mantle in the Ouachita, there is no reason to believe there was a lateral flow of the mantle under the Ouachita. So the crust and the upper mantle are probably coupled. So if I understand what you're saying is that the crust and the mantle have the same age. So they are coupled. So there is no reason why that mantle should have moved away from under the Ouachita.
In terms of preservation of the scars, are you referring only to the lithospheric mantle and not the asthenospheric one? Because I would imagine that in the asthenosphere, probably not preserved much.
I would imagine that definitely doesn't get preserved, right? I mean, that should participate in the convection. So that definitely.
Right.
No, I'm talking about the continental lithospheric mantle. Yes, because so when the images, the seismic images I shown, those are 90 kilometers depth. So we are in the lithospheric mantle. So yes, not beyond. Yes.
Any insight into as to, for example, like the models, some of the models proposed for the Alps, where we had subduction along the active subduction zone, resulting in mountain building eventually and closure of an ocean basin, that kind of stuff. But then, in order to exhume those very high pressure rocks and
Right.
something like that. Do you see any signal there? I mean, do you have any insight
Signal
as
of
to-
inheritance?
Of inheritance as far as the
I think that there is documented inheritance along the Insubric line, for example, following the pre-existing opening of the Tethys that I know in literature, if I remember well.
About, for example, taking the same subductions or the same active subductions and reactivating that
For the
exhumation.
for exhumation
Does that fit?
or abduction,
Do
yeah.
you know of any?
No, no.
Did you still say?
Go ahead. Go ahead.
The events causing a grid.
The new med.
earthquakes are still missing.
We don't really know what is causing the earthquakes. So there are working hypotheses. So the elastic rebound that follows the retreat of the glacier is one of the hypotheses. There are many other working hypotheses. So the idea that, or for example, erosion of focused erosion from the Mississippi River in a certain area, again, removing a load on the top of the lithosphere and therefore allowing the lithosphere to rebound up. You know, imagine the lithosphere is like a mattress that, and you put a bowling ball on top of this mattress. You know, you remove the bowling ball and the mattress rebounds back. So as it rebounds back, you know, that releases a stress or perturbs the stress of a crust and lithosphere that are under, you know, near failure. And so the faults are perturbed and they fail. Why, you know, so that will provide an explanation as to why now and why there. Because obviously the rebound should affect everywhere in North America because the glaciers and the ice sheets was everywhere in the North American region, right? So, but why only there? Why we observe the new Methodist seismic zone only in the area that we observe it today? In order to localize deformation and seismicity in that area, we use the rift pillow. That is the structure that is capable of focusing deformation there. So it's the combination of having a specific crustal structure or lithospheric structure and the stress perturbation together cause deformation in that region. But now we are seeing that there is probably deformation even outside that area. So obviously we have to change our geodynamic models.
Maybe that means that's the deepest or the thickest point in time.
But we don't know. So we're going to have to just go and see, you know.
I thought it was interesting, trying to pick out what exactly my question is here, but I thought it was interesting that compared with the Yavapai mountain sol structure, the lithosphere mantle under that and the under the seismic zone, one was colder, right? And the Yavapai had these sort of spots of hot. And so does that affect, it seems like to me that affects what type of tectonic activity is now there in the present day. Under the grid, it's all earthquakes, potentially because of more brittle lithosphere mantle there. And then under the Yavapai moss, it's all sutures. It's warmer, and so there you have like volcanism and very young volcanism. Do you see any, I don't know, just anything else interesting like that?
Well, you do have a lot of earthquakes. You know, I have a map of the earthquakes in the United States, and obviously throughout the Western United States, you have a lot of seismicity, right? You know, that is, I will almost call it a diffuse plate boundary in a certain way. So.
I mean, I still look at, you know, the Rio Grande Rift as being an active part of the boundary, right?
Right, exactly. So the Rio Grande Rift is actually, you know, coming north-south, and the Hermetz lineament is converging with it on the front of the Rocky Mountains. Here you have obviously the effect on the Hermetz lineament. You have the effect of the fact that you have a very high tectonic area, and that you have a thermal anomaly associated with all the tectonic activity that has been happening there. Now, it is interesting that the mantle is like penetrating the old continent, and in order to penetrate the old continent, is almost disassembling the continent along the same grain that it is being assembled along, right? So that's the grain of the assembly structure, and the continent is being disassembled along that. Because to the north there is the St. George lineament, and to the north, there is the Yellowstone hotspot that is following the Wyoming sutures. So.
What are the next areas of study in the United States, and what do those areas help to prove for these conclusions?
What are the next area?
Yeah, regions in the United States.
So, there is activity. So research is, it's everywhere in the United States. So there is a project. The GeoPRISM project has the east margin of North America as one of the focus sites. So this data set that we just acquired is open to everybody for analysis. And the entire margin is an area that is open for analysis. It's called focus sites. In North America, the Earthscope is now moving. Earthscope is an initiative supported by the National Science Foundation that has imaged progressively from the west coast to the east coast by using swath of seismic stations, 400 seismic stations moving from the west coast to the east coast. And it's been imaging the mantle and crust throughout the 48 states, and now it's moving to Alaska, for example. That is the new frontier, where we're going to be seeing, detailed images of our North American continent. And but anywhere you think, any research question could be answered, NSF. Or any other, the USGS might be interested in funding research, as long as the question is interesting and worth funding. It's worth collaborating with other people. Each of these projects was a multidisciplinary, multi-institutional collaboration. So nothing that I did by myself. And as you see, so it required the collaboration of people with different expertise. So, for example, this one here, the ENAM community experiment, we are bringing together different institutions. So we have broadband OBSs, and I'm going to talk more about this this evening, on how we did it. But we have broadband OBSs, so you need passive source seismologists that operate out at sea. And we have short-term active source OBSs. So these are, again, it's a different type of expertise that you need always at sea. And then we have multi-channel seismic reflection data acquired out at sea. Again, a different type of discipline. And then we recorded refraction profiling on shore. So again, a different type of expertise. And so all this just to acquire, and this is all within seismology. So you require different type of seismological expertise just to acquire a project like this that spans the shoreline from the continental crust into the oceanic crust. And then projects like the CDROM require this type of expertise plus geochemists, structural geologists, and more. So the key here is to collaborate.